Okay.
Yeah, that's a mistake. It should be up to here. Yeah, it should just be representing the amplitude. Yeah, doesn't extend to the cosine term. Thank you very much. I think it just the line extended. Yeah, but it doesn't. Thank you very much for that, pointing that out. So that is the output ASK signal. So for ASK, we use RZ because you're going to find that for the same, for I think for the phase, we are going to use NRZ. It will actually be almost the same arrangement. So for the detection, it's very simple. This is an ESK detector. So you have your ESK signal. You can see your signal is in the envelope. Yeah, your signal this envelope. Yeah. So you're going to have simply an envelope detector. So you have a rectifier. It's basically an envelope detector. A rectifier to cut off the negative side, so that, yeah, of course, this envelope. Oh, you won't just add that envelope, so you have to cut, you have to rectify so that you only have the upper one. So you're interested in this envelope that will generally give us the signal. So you have a rectifier, then of course you have the LPF. LPF will remove the carrier and only leave the um, low frequency signal. It will remove the high frequency signal. So we use a low frequency filter, yeah, low pass filter. Yeah. And then of course you go to the comparator. The comparator is the decision circuit. It works on a certain threshold. If the amplitude is a certain, or rather the energy is a certain level, that's a zero. If it's a certain level, is a one. Yeah. FSK, this is just like before. This is the analytical expression for the, oh, uh, FSK. I think sometimes is FSK. In this case, the this is a varying quantity. This is a quantity you are going to change, Wi. So in this case, we have I to M, and the frequency uh, term, the frequency term again has M discrete values. Sorry for this. I think it's because I was just getting one and copying onto the other one, and I forget to delete some things. So the frequency term has M discrete values. Yeah. Advantage, yeah, because this is what is varying. So this goes from I to M. So it depends on what is M. If M is 2 is binary, M is 4 is quadrature. So M can vary up to any value. Yeah. Advantage is less susceptible to errors than ASK. Disadvantage is that it uses twice the spectrum of ASK. Yeah, because you are the frequency, you have to use two frequencies. So we are assuming if you're using the same frequency, then it will be twice the frequency because you have to use two frequencies. Yeah, which in the other case, you're only using one frequency. You're either switching it off or on. Yeah. So that is that is FSK. You can see the frequency for 0 is lower than the frequency for 1. Here they are occurring for a particular time. You have uh, more repetitions. Yeah. So that is FSK. How this is how you generate it? Binary input, binary digital input, and again, this would be something from again, this will just actually be a signal. Although we don't draw most of the signals, sometimes we just put binary digital input. Again, this will be a signal representing the 0 and 1. Yeah. So that signal, whatever it is going to switch actually this one should be an NRZ. Yeah. So if you have a negative, if you have, let's say, this waveform, that is going to switch. This one is going to switch. The first frequency is maybe frequency for, let's say this is for 1 and this is for 0. Yeah. Representing 1 is presenting 0. That is NRZ. So you have this. When you get this, it's going to switch on this. But here is going to be inverted. And what thing is, this is not going to switch. You only, it only switches, it's positive. So if you have your oscillator being switched on by a positive voltage, then it means this will not switch on. So for if it is a 1, it will switch on F1. And this is inverted, so it will not switch on this one. Yeah. You can look at it from a point of view that if you are switching this, say, with a 5 volts signal, then this will be -5, so it will not switch it on. Yeah. If you having a 0, then it's negative, then that will be changed into positive, and it's going to switch on this. So that's how it works. So you have a limiter. It's a very simple mechanism. So you have 0 and 1, and they will switch to different oscillators, and then the output is a combination of it. FSK non-coherent detector is this one. This one means you are not going to generate the phase of the carrier at the receiver. So this is your signal input. You have a bandpass filter. This one simply filters. This filter is tuned to F1, and this filter is tuned to F2. Yeah, and then you are trying to get your signals out. So all you have to do is just get the envelope of that of your signal, and that is going to give you just get the envelope of the different signals after you filter. Yeah. So FSK be non-coherently detected. Remember I said ASK and FSK can coherently detected. PSK cannot be, but DSK, differential PSK, can be. You can also use coherent. So whenever you talk of coherent, it means we are able to detect, we are able to generate this, because this has to be in phase with that was used at the other. So we have a cosine and no, we have the two oscillators. These have to be in phase. What was emitted. So although we are putting it this way, actually the generation mechanism of this is quite complex. You have to have complex phase sine wave generators. I mean, sine which is actually in phase. I'm going to look for the correct name to call them. Yeah, so you need that. then you are using a multiplier with this, you can mathematically work it out. If this, for example, was a cosine, because what you use is a cosine, to replace, instead of even having two frequencies, you can have a cosine that's a sine. So if you have one frequency and multiply this, receiver, so which we are going to look at later. So then you use the BPF, the bandpass filters, for the different frequencies. In this case, you're not using cosine and sine, you're using different frequencies. But you're going to see that if you just multiply with the different frequencies, of course, and then filter, you're going to get your your binary signals. Yeah, I think that one will become clearer when we go to receivers towards the end of this course. Phase shift keying. So again, the term has M. Yeah, is okay. So here we are looking at the phase. There we are. So these are the different. This is the different values of phi IT. I is varying from 1 to M, and M depends on depends on your modulation, whether it is binary or whether it is binary or is using, you are carrying 2 bits at a time, or 3 bits at a time, or 4 bits at a time. Yeah. So in the case whereby it's binary, of course, what you're going to have is I is equal to 1 and 2. So you're going to have, when it is 1, this becomes 2 pi over 2. So you're going to have pi. And when M is 2, you're going to have 2 pi, which is basically 0. So if you have only, if it is binary phase shifting, so you're going to have 0 and pi. If it is quadrature phase shifting, where M is equal to 4, so you're going to have 2 pi 1 over 4, 2 pi 2 over 4, and you're going to have 2 pi 3 over 4, and 2 pi 4 over 4, 2 pi 4 over 4, which is just 2 pi. So generally we are going to have pi by 2. And this is pi. This is 3 pi by 2, and this is 2 pi. Yeah. So that is a phase. So it depends on M. So if you are carrying 3 bits, yeah, I think I hope you are okay with that. You have done that already. Or when I talk of carrying 3 bits, what we understand what you mean, because when you're carrying 1 bit, that's a binary. If you're carrying 2 bits, that is now this case. This is the binary case. Yeah. But again, we are going to look at that when we look at multi-level signaling. So that is this is your data, and this is your phase. You can see in this case you have 180 degrees phase change, 180 degrees phase change whenever you change from 0 to 1. That's the generator. You can see here we're simply using a multiplier, and here we have your binary sequence, which is represented. Actually, this is where we have the none return to 0. So we are using the same multiplier as in the ASK, but in this case, we are using a none return to 0 as opposed to return to 0 in the case of ASK. That is a coherent detector for BASK, the binary ASK. So here you receive signal, and we have your cos WCT, which of course whenever you hear that whenever you hear of coherent, because this is coherent, it means you have to generate that at the receiver. And what we are doing is, when this is a cosine and then we integrate over a period, and then is only when this is corresponding to the we are assuming here, of course, yeah, this was a cos W, yeah, this was cos WT. So we are only saying that when this signal here is something cos omega CT, because whatever it is, it will be having the message, but it will still be having the cos omega CT. So it's only when you have cos omega CT multiplied by cos omega CT, and you integrate over that period, that you are going to have an output. Otherwise, in other cases, you are going to have 0. Yeah. So that's why it will be detecting the 1 when you have cos omega CT, and 0 when you don't have any when you don't have cos omega CT. Yeah. So that's the binary output. We are going to use the same principle when it comes to quadrature, but in that case you'll be having cos omega CT and sin omega CT. Yeah. I hope everybody is okay. I'm assuming you have done this before, so that's why I'm moving. I think I'm moving too slow. So constellation diagram. This is just a representation of a signal modulated by a digital modulator, or digitally modulated on a scatter plot. So this is very important to us, especially when you are doing noise performance analysis, which we won't do, but it's very important because it helps you understand why certain modulations would have a poor noise performance. Yeah. Because like in this case, you can see when you have 0 and pi, you have the the largest Euclidean distance between 0 and 1. What it means is, to change a 1 to be received as a 0 in PSK, it means you have to distort the phase of this signal by 180 degrees. Well, not 180 degrees, anything above 90. Of course, if it goes above 90, then it will be considered to be a 0. So you can see you require quite a lot of phase change to get here. And of course, it will make sense, because if you have QPSK, well, QPSK ideally it should be starting with, well, it does, yeah, should be pi by 2 pi, but usually we don't use that. We see later why you get 45, 135. It should be 215. I think they should be, no, 235, 315. Yeah. So you can see this is actually very close, because to move from here to here, you just need a 45 degrees change. and then your signal can be mistaken with this. So this scatter plot actually does give us an idea of how each system performs in the presence of noise. If you have 8 PSK, of course, you would have more, yeah. In that case, would that be 8? Yeah, I think that is. Well, if you want to look like that exactly, if it's 8, then the spacing will be different, yeah. But if you have 8, it means they are now still even closer. That's why actually once we go after 8 PSK, we don't use PSK, now we go to QAM. Yeah, we already use 16 PSK. We use 16 QAM because it has better performance in the presence of noise. Advantage, of course, is PSK is less accessible to errors than ESK, while it occupies the same bandwidth as ESK. Yeah, remember you're only using one waveform and frequency. More efficient use of bandwidth, higher data rate is possible compared to FSK. Yeah, of course, this higher data rate is possible because you can use the same carrier, same frequency, only change the phases. Yeah, you can do it, but it also means you need more bandwidth in terms of frequencies. Yeah, when you're using FSK. Yeah, it is more complex. Signal detection required. Remember, you said you must have coherent. So that's a disadvantage. More complex signal detection process. It's complicated by the fact that you have to generate the carrier at the receiver. Yeah. Differential phase shift keying modulation. I think this one you are trying to it's just an alternative to the PSK. You use the phase, but you don't require to generate your carrier. You don't have to have carrier phase recovery. Yeah, this is what I'm looking for. You don't need carrier phase recovery circuits at the receiver, yeah, which is a big advantage. So you can simply use an incoherent receiver. Yeah. So in this case, each symbol is modulated relative to the previous symbol. So it is what we call differential. It's like differential encoding, differential PSK modulation. So it's very simple. That is the circuit. What you are doing, you're just using an X NOR gate. We have an input. It means once maybe you are putting a 1 and followed by a 0, followed by a 1 like that. What will happen is when you put a 1, this is a 1-bit delay. So by the time you get 1 here, it means when the 0 comes, you are actually now combining a 1 and a 0. Yeah, because this will be a 1. Yeah, remember this is coming in the next phase. I mean, in the next bit. So after 1 bit, you're going to get to the next bit will be combined with this because there's a 1-bit delay. Yeah, this one is here is delayed by 1 bit. So the time it arrives here, it arrives with a 0. So you'll be comparing. You'll be inputting the XOR, XNOR with the 0 and 1, and you will see this actually gives you the PSK. Yeah, you can do the exercise and see how this is generated and how it's now possible to reproduce that at the other end. Because at the end of the day, what matters is that you're able to reproduce your original bits if you use this circuit. That is something you can work on. You can try to see when you're using XOR what it means if you keep on changing bits, and then you just use a multiplier, and no multiplier like in the multiplier like in the PSK case. Yeah. So I hope so far so good before we go to the MRE signaling case. Yeah. Any query on this one? So in MRE signaling case, of course, in the binary, we have been having two symbols. Now we are going to have more symbols because each symbol will be carrying more than one bit. So if you are carrying two symbols, and of course it makes sense because if you have got, let's say, let me fill these gaps, and every time a symbol just carries one bit, it means that is in the binary case. Then it means the bit rate is the same as the symbol rate. Yeah. And remember, when you signal at a very high rate, the limitation in circuits is not the bit rate, it's actually the symbol rate. How much the signal is changing. That's the frequency. How much the signal is changing. So if you are dealing with most electronic devices, most diodes, transistors, as the frequency goes up, then the the capacitive resistance, yeah, goes. I think it goes capacitive resistance. Does it go lower? Yeah. So at very high frequencies, sometimes those devices become like shorts to high frequencies. Yeah. That is because of 1 over omega c. So as the frequency increases, and it does increase, because the frequency is increasing. So I'm actually trying to look for the word. Kind of the built-in capacitance. If you remember the word, you can remind me. There's a word for it. Is it parasitic? But that inbuilt capacitance. This is not a capacitor, but you have some inherent capacitance in most of the electronic devices. Yeah, it happens in all communication systems, even in cables. Yeah. So as the frequency increases, that capacitive value, although it is small, it becomes, because of the omega, it becomes quite significant. And in the long run, you cannot go for higher frequencies. But if that signaling rate can remain the same, but for each signal carry more symbols, carry more bits. Yeah, that's the whole concept behind MRE signaling. Yeah, so with one signal change, if it's 16 quam, you are carrying 4 bits. So if you carry 4 bits and you're having 16 quam, it means 0000 is carried by one signal up to 1111. So you have 16 different signals. So you have 2 to the k possible signals, each representing k message bits, where k is an integer. What you want, yeah, that's the whole idea. So you have S1 M, S1 T to SMT, each representing k bits to be transmitted. So bit rate is equal to k multiplied by symbol rate. Symbol rate we also call it baud rate. So Quam, in Quam, what you have is, I think we just go directly to, uh, we just go directly to what you can see it easily into the how you generate Quam. This is how you generate Quam. Well, uh, this is how the Quam works actually. So you have your binary input at this rate, 1 over TB, and then we have a serial to parallel converter, which means at each time we are taking 2 bits and directing them to different modulators or multipliers. Yeah. So we are creating I and Q. What it actually means is maybe you have this. So that is the I, the next I is this one, the next I is this one, and this is a Q. This just means in phase, and this means quadrature. Quadrature is because you use the concept of cosine. One you multiply the cosine, and the other one you multiply with a phase shifted. This is a 90 degrees phase shifter. A phase shifted cosine. It's produce a sine. They are just shifting by 90 degrees, and so we call this the Q arm. Yeah, and this is one the I arm. Because this one is the in phase, we are considering cosine to be in phase, and sine to be the quadrature. It is 90 degrees of the cosine. Yeah. So you have that, and of course that you combine the output, and that's what you post. That's a QPSK signal. The concept can be demonstrated very easily here. So here you have your 0, 0. So 0 is represented by a minus cosine. It makes minus cosine, what we are saying, and a minus cosine, and yeah, because here 0 and 1, now 0 will be maybe minus, and 1 will be plus. Yeah. So when you have 0, 0, 0, you have minus cosine and minus sine. We are saying we have got 0 here because 0 is a minus. If you have 0 here, then you'll be having minus cosine. And if you have 0 here, you have a minus cosine. So you have 0, 0, you have minus cosine and a minus sine. And you combine these two. If you have 0, 1, of course, you have a minus cosine because it is 0. But this one, you have a plus sign. If you have 1, 0, you have a plus cosine and a minus sign. And if you have 1, 1, both are plus. And when we check the waveforms, we'll see that there will be maximum at different uh, uh, what do you call it, at different angles or at different phases. Yeah, so you're going to find this will be maximum around where is it, trying to see the resultant. Yeah, this is it, trying to interpret this. So the resultant waveform is this one. Yeah, this is the resultant waveform, this one. So you can see where it peaks. Yeah. So is a maximum here. This will be this one case, the resultant waveform. And you see at the different. So this resultant waveform is actually what represents, is what is going to come out here. I'm going to identify the 4 places, the 4. So the first one is here, which is 45. The next one should be 130. Oh, this is 0. Yeah. Then there is this. This is on 135, and the next one is here. Where is that? Oh, here. Yeah. Oh yeah. Of course, this is how the resultant is varying. This should be this should be what? This should be this 145, 135. I'm unable to interpret my own drawing here. But well, you can see now the resultant, of course, varies, and that is now the variation you transmit. And in this log, that's the variations you transmit, and that's what you reject at the other end. I was trying to interpret this, but what you are seeing is this what results when you combine these two, and you can be able to detect. It will give you different values at different uh, times. So that's the constellation diagram for QAM, for 4 QAM. This is not 16 QAM, this is 4 QAM. Which is the same as for PSK, because PSK is in this case, this is not for PSK. This is for QAM because we are using both. Well, actually, this is for PSK. It's for PSK, but we have used the code, the QAM. We have used the QAM method to generate for PSK, but actually you can see it's for PSK because the amplitude is the same. So it's not really for QAM. But sometimes we call it for QAM because you have generated using the QAM method. Yeah, where both amplitude and um, and phase. So we have used the QAM method, but it's basically a 4 PSK because the amplitude is the same. It's just one. That's amplitude. It's just one. Yeah. Uh, they have the same amplitude. So basically, you can say it's just for PSK, although generated using QAM method. Yeah. So I think the advantage of using QAM, of course, it carries more bits per information symbol. Yeah. Of course, that increases spectral efficiency. Mm. We know, of course, they are susceptible to noise. Yeah. Yeah. This I think I talked about already. I think this one we are okay. Well, this is offset coordinate shift key. I think all you're doing, we are introducing. Okay. What happens is, of course, with the QPSK, maybe I should just tell you a few things. One is you always make sure that you use the gray coding so that you don't have what you're trying to avoid is any adjacent symbol, the one which is closest to result in 2 bits change for obvious reasons, because it is easy at the receiver to mistake this for this than it is this for this, because these are very far from each other. These are 180 degrees change, but it is easy to get this change if you have something. If there are certain conditions that can change the phase of the signal, then it is easy to change to this one. In any case, you only require to change to our phase change of more than 45 degrees, and then of course this one, the receiver will think it is this signal. Yeah, if it is here, that will be ambiguous. Yeah. So what you do, try to avoid 2 bits change. You can see from here to here, there's only 1 bit change. This bit remains the same. Only this changes. Yeah. So you want one uh, one symbol error not to generate 2-bit errors. Yeah, because if you mistook this for this, you only get 1-bit error. Only one error will be only one bit will be an error. So you always make sure in the positional diagram that you don't have 2 bits changing. You can see between here and here, this does not change, only this changes. Between here and here, you can see this changes, this does not change. It's very important. If you have to do the constitutional diagram, just remember that one thing, that you don't want 2 changes. Because if this was 111, this was 00, and then there was a symbol error, actually 2 bits will be in error. Yeah, and we try to avoid that. Yeah, that is one. The other thing is we want to avoid some changes. When both change, you can have both changing. See what you mean is you can have 00 followed by 11. So that will be one. Oh yes, yes. Has somebody, is that somebody raised the hand?
Yeah, I have a question concerning
Yes.
the importance of generating the phase of the carrier signal at the detector. That's what advises the design of an uncoherent and coherent detector. Yeah. And
The question again, please. What I just explained. Oh,
I was asking
uh,
what advises the design of a coherent or a non-coherent detector, or in other term, what's the importance of generating the phase of the carrier signal at the detector? Yeah.
oh, I see, I see, I see. Well, uh, why is it important that you do coherent other than uncoherent? Actually, it is a noise performance. Yeah, that we need to do actually the noise performance analysis. You find that coherent has got better noise performance. Uh, I don't know whether it's any better way of explaining it, but if we are not doing the mathematics of noise performance, but if you do it, you're going to find that. I'm trying to think whether there's a simpler way. You're going to find that the coherent receivers perform better, but I'm trying to look for an intuitive um, explanation to coherent why it's important to use coherent where you have a choice, of course. You see, with the PSK you don't have a choice, you have to be coherent because our message is carried in the face, so there it's very important. So I think your question is where you have a choice, why would you? It's simply noise performance. Yeah, and we would have to do the noise performance analysis for us to really understand exactly what that means in a case where you can use any of them. Did I answer your question?
It's okay. Thank you.
Yeah, it's just noise performance, but it's not very obvious until you do noise performance analysis to see that actually it performs better in the presence of noise. Yeah. Uh, I think we have used Quam. What I was trying to explain is if this happened, if this happened, you'd have a phase change of 180 degrees. Yeah. If your signal was this, then the next one was this. There will be this phase change. Now, the problem, of course, such a phase change, again, you have to go back to the type of amplifiers we use. It means once you have that, you cannot use non-linear. You cannot use a non-linear amplifier. To handle these kind of changes, you need to use a linear amplifier. I think you generate a lot of, if you use a linear amplifier with that kind of phase change, you generate a lot of harmonics. Yeah. So we can't do that. So we avoid by all means to get that kind of change. And how do we do it? Is to make sure that we don't have both arms changing at the same time. So we create a delay in the queue. So you can't have two bits changing at the same time. Yeah. So you can have that OOPSK. So that's why you have the offset QPSK by this offset. So you are having your signals, the ones representing zeros and one. So there will be 1 bit delay. So it means something like that. So there is a 1 bit delay. Yeah, that's what we are saying. So you not have them changing at the same time. Yeah, by having this. So again, it's the same arrangement. The only difference is that. Yeah. And I think this is a mistake. This is not supposed to be minus. This is simply supposed to be sine omega t. Just a phase shifted. I don't know how I got this minus here. Yeah. QPSK demodulation, there you are. That's a QPSK demodulation. This is the received signal. You have the cos omega t and this sine omega c t. So remember here we had done, the difference between the two is cos one is modulated with cos omega t and the other one is cos omega ct. So you want to know whether this side is 0 or 1 and whether this side is 0 or 1. Yeah. Yeah, then you combine, because this is 2 the bits. Here is you'll be getting 2 bits at a time. Yeah. So here we are. So what you're doing, the signal goes to both arms. One is multiplied with a cos omega ct, and the other one is multiplied by a sine omega ct. And depending on whether what was coming in had cos omega ct, omega t, and then is sine omega t. This is what I was trying to explain before. So if you have cos omega t multiplied by sine omega, if you have sine omega t, because remember you have sine omega t in both sides. So if you have sine omega t, then sine omega t times cos omega t integrated over this period, you are going to get the output as 0. So this sine omega t, you can do mathematically actually, you can do arithmetically, you can see it. If you have sine omega t times sine omega t integrated over the period, is going to give you some value. Yeah. That's actually the simple principle. And then of course you have a threshold detector to decide whether it was a 0 or a 1, then you're going to have your output here. It's just that one you can do mathematically, calculate, you're going to see that actually is the whole principle. Because whatever the signal it was, it will be something, the signal which could also be time varying, yeah, sine omega ct, yeah, or cos omega t ct. So whatever it was, and that is what just uses that. That's what basically is the coordination receiver, yeah. That bit, yeah. So So I think we have explained what we were talking before. We are preventing 180 degrees transition. That's why we are shifting one stream by 1/2 bit period. It's not 1/2 bit. This should be by 1 bit or half symbol period. Not bit. Half, this should be symbol. Either 1 bit period or half symbol period. I think it's good to put that there. So it's 1 bit or half symbol. 1 bit change between transitions. Yeah. Minmap shift keying. Actually, this one is best.
Excuse me.
Yes.
I was asking whether the detection of QPSK,
Yes.
the integrator in the circuit, can it also be used as a low-pass filter just to filter the high frequency signals and then allows the low frequency signal to pass through to the detection side?
This circuit.
Yeah,
Can it be used as a filter?
as a low-pass filter, maybe just filtering out the high frequency signals and allows the low frequency signal to pass through to the detection side.
No, because this one, you see here, we are relying more on the phase. This QPSK, because of the P, we are relying more on the phase and not the frequency. Does it make sense? Actually, this is the same signal, only the phase is different. So it's a certain signal and this phase shifted. So it's the same signal, only phase shifted. So we cannot use just a filter.
Okay.
Is that okay?
Yeah.
Okay. So here, MSK is basically what we call a continuous phase frequency shift keying. It's similar to OQPSK. Actually, this is more of a frequency shift keying. What you're doing is you want continuous, you want to avoid continuous, you want to avoid phase shifts. I'm trying to see which is the best. Oh, maybe this is ends here and this one starts here. Yeah. This is what we are saying. You want this continuous phase should be like this, then it continues. Yeah. It's something similar to what you do with the what do you call it? With the class B amplifier, where you have this coming from one bit, this is coming from another bit, but then you want them to, you don't want there to be a discontinuity. You're trying to avoid these discontinuities. Yeah. Actually, we are trying to avoid discontinuity, so we create what we call continuous frequency shift, continuous phase frequency shift keying. That's what we are trying to avoid. Yeah, we have just made it simple. Otherwise, this one is we can actually show with diagrams why this how this is done. But let's just know that what you are trying to get, other than even how it works. So there are no phase discontinuities because frequency changes occur at the carrier zero crossing points. You want your changes to occur at that as you are crossing. So you want changes to occur there. So there will be continuous phase. That's what we are talking about. We want to avoid phase discontinuities. That is the whole idea. Yeah. Because these phase discontinuities end up creating harmonics, sidebands. Yeah. Outside the allowed bandwidth. So you don't want those sidebands. So you avoid this phase discontinuity. Again, this one, unless you go back to the mathematics, is it may not be intuitive. Yeah. So MSK is encoded such that the Q component delayed by half the same way, and each bit is encoded as half sinusoid. That's the only difference between this and OQPSK, is that each bit is encoded as a half sinusoid. Yeah. And also, the difference between the high and low frequencies identical to the half bit rate. Yeah. It's quite a mouthful. I think don't give it so much about, because I know you will not be able to understand it until you actually taught this. And I didn't. I think I tried to make it a bit simpler. So a Gaussian MSK, why I mentioned it, because this is what is used in GSM. Yeah, it's used in GSM, the precursor of the 3G. Now you know we are not even in 3G, now we're in 5G. Yeah, but in GSM, this is what was being used, the Gaussian MSK. It simply means that before you take your signal to the MSK modulator, you first of all use a Gaussian filter. Yeah, with a sharp cutoff. Yeah. So I think here we are trying to improve the spectral efficiency. We are removing. We are trying to remove some parts. We are trying to remove. We are trying to pre-filter the signal before it gets to the MSK modulator, and we use the Gaussian filter. I think that's what. So advantages, of course, improved spectral efficiency when you compare it with other phase shift keying, because remember it's a continuous phase frequency shift keying. It's an FSK, yeah, but so it has better spectral efficiency. They can be amplified by nonlinear amplifiers because we have removed the discontinuities, and of course is better than ASK. This one already have discussed, being FSK. So it has all the advantages of an FSK, advantages of a continuous phase. Yeah. So far, so good. Except for this one, don't give it much thought. It is best understood if you go through the mathematics and actually plot this. So for now, just take, I like explaining everything to the detail, but this one just understands that what we are trying to avoid is phase discontinuities. So we do something similar to what we do in the OQPSK, and in this case, we use a filter before getting into the MSK. Basically, a Gaussian filter in MSK. 16 QAM. So here, this is 16 QAM. I think the best way is to look at it from just from the drawing. So here we are taking 4 bits at a time. Remember, we are trying to have 4 bits represented by one symbol to improve spectral efficiency. Because I said the limiting factor normally in communication circuits is a frequency. is a signal change. It's a signaling changes. That's why you try to carry as many bits as possible with each signaling changes. But of course, it has its own shortcomings in that now it means the symbols are so close to each other that so close to each other in that constellation diagram that you can see that it is very possible that one symbol can be mistaken for the other one. But remember again, here we still use the same thing. We make sure that no symbol change, the most likely one, can result in more than one bit changing. Yeah. So what you have here is you have got your 4 bits at a time. So basically, this is what we call a serial to parallel converter. But here we are taking Q1 and Q2 symbols. So if you're having 1011, it means you put 10 here and 11 here. Then you have 2 to 4 level converters. This one is a very simple mechanism. What it is doing is just the value of the modulation of the input to the modulator. So normally we use two voltages, and you can have, let's say, one. What would be the best representation? Some voltage V1. You have 2 voltages V1, and then you have the minus V1 and V2, and then we have minus V1 and V2. So I think 0, 0, you can have 0, 0 represented by minus V1. Yeah. By V1. Let's say by V1. And 0, 1 by V2. Or let's say minus V1, minus V2. 1, 0 by V1 and 1, 1 by V2. Actually, if I remember the voltages, normally it's about, I think it's 0.22 minus 0.22 minus 0. The PSK uses, I think, point something, 0.8 something. Can't remember. Then the other one is plus 0.22. And this one is plus 0.8. I don't remember it's 0.8 what. I think that is one of the most common at this. So you are creating from this, you have 2 levels, and you are creating 4 levels. These are the 4 levels. So you have 4 levels, and so you'll be combining. So if you have got 4 levels, and here 4 levels, because these 4 levels are modulated with the 90 degrees phase shifted, which is basically a sine. If this is a cosine, this is a sine. Yeah. So you have 4 by 4. So you give, if you have got 4 combined with 4, then you have 16 possible combinations. So that's how you get the 16 different possible combinations. Then you have a summer, and that is the output. That's how the PSK, that's how the 16 one generates. The only difference with the quant is this part. With the 4 quant or QPSK, it's basically this part. First, because you're taking 2 symbols for I and 2 symbols for Q, and then from the 2 you're generating 4 levels each, so it can be 16. That's a constellation diagram of 16. You can see whatever is next, only one change. You see from here to here, only the one bit is changing. From here to here, only one bit is changing. From here to here, only one bit is changing. Even here to here, only one bit is changing. That's how they are arranged. Yeah. To make sure whatever is close, whatever is most likely to change to, cannot result in a higher bit error rate. Yeah. Because at the end of the day, when it comes to error correction, which we are going to do next semester, the error correction works on the bits. It corrects the bits. So you don't want to, some of the systems will be limited to maybe only correcting one bit in a sequence. One bit error. One can only correct if one bit is in error in a sequence. Yeah. So you can see the importance of sometimes not having too many bits changing. That's why we got against that. So I'll stop using my mouse. That is, here we are comparing the performance of different modulation formats. We are not going back to, we are not going to the, we are not going to the performance analysis. So we are just giving the figures. So of course, QPSK bandwidth efficiency is 4 because it carries 4 bits per symbol. 16 QAM the same, 16 PSK and 16 QAM the same. This is PSK for is 3 bits, and PSK for PSK is 2 bits, for QAM is 2 bits, and this. But when it comes to error-free EB to N naught, yeah, remember we are talking about this ratio. Error-free EB to N naught. This is this requires a higher. You can see you require a higher signal to noise ratio. Yeah. So the better is the one which is better is the one that requires less signal to noise ratio. Yeah. For error free. So for this to be error free, you need the signal to noise ratio to be 18 dB. Very, very high. It means it's accessible to errors, and it makes sense. Yeah. 16 QAM, you require this to be the signal to noise ratio. 3 dB lower to get error free. Yeah. But you can't do as well as this BPSK. Actually, it's interesting because the low calculation, you can see that for QAM and for PSK, actually why they are the same is because the 4PSK is implemented in QAM, using QAM. Yeah, the implementation is using QAM. So although if you look at it, it's basically just 4PSK, yes, as I explained, because the amplitude is not changing. Yeah, and you can see compared with the BFSK is bad. But you can't compare this with this. This one looks like it's performing better, but of course it's spectrally inefficient. So there's a balance between spectral efficiency and noise performance. And you can see why we were using EI in the amplitude, because I mean in the difference in the different analytical expression. Yeah, we're using that because this is a very common metric when it comes to digital communication. Yeah, that is the energy per bit. Yeah, divided by n naught. This is the noise. Yeah, so that is all about uh, digital career motivation. Do you have any questions on this one? If we don't have any questions, I think we can just start looking. We'll continue in the afternoon. We can start looking at the Z transform. From yesterday's discussion, it appears like Z transform is important in this in your labs. So let's go to Z transform. I'll stop sharing. Then we can look at it for the next, let's say, 15 minutes. I think that will be okay. So that now in the evening we do also less time. We do 1.5 hours in the evening. Is that okay with everybody?
Yes.
Ah, very good, very good. So let's see the Z transform. My mouse is working. So that is a Z transform. Basically converts a time signal into a sequence of real or complex numbers. Signal into a frequency domain representation. That's what DTFT does. Yeah, it converts a discrete time signal, a sequence of real or complex numbers, into a frequency domain representation. So this one is actually a very important tool, as we are going to see, of analyzing interaction between signals and the systems. Uh, uh, Sorry about this. It's going to move my mouse. I need to buy a new mouse. Yeah. So this is a two-sided, the bilateral Z transform, which is defined by x of z, and goes from negative infinity to infinity, x of n, z to the minus n, where n is an integer and z is a complex number. So because z is a complex number, all you have done is we have just, instead of now breaking the complex number, we are just looking at z. So unilateral varies from n is equal to 0 to positive infinity. Actually, Z transform is actually is Z transform in discrete time. is actually the equivalent of Laplace in a continuous time. Yeah. So comparing with dTft, you find that dTft is defined as x e to the j omega n is equal to negative infinity x of n e to the minus j n as a definition of x of dTft. And the z transform is simply the same, but what we are doing, we have this x of n multiplied by r to the minus n. So x of z is simply the dTft of x of n r to the minus n. We are going to say that r now, depending on the value of r, this can either converge or diverge. Yeah. How is z transform applied? We are going to see that z transform is very important when it comes to difference equations, because when it comes to describing discrete time systems, you can use the impulse response. You can use the transfer function, or you can use difference equations. Yeah, and we are going to see how Z transform works with difference equations. Remember, you are using the Laplace of the differential equations because it makes it makes differential equations easier when you use Laplace. But yeah, same here. To convert difference equation describing a system into simple linear algebraic equation, making analysis easier. Now this will be very easy to see. Plot poles and zeros on the complex plane for stability analysis. Yeah, you can plot your poles and zeros in the complex plane. Yeah, that becomes very good because you just be dealing within. We are going to see you're going just to be dealing with that complex plane, and it's easier than when you deal with the Cartesian, yeah, with x and y. Used to create transfer functions for digital filters. That's what we are going to do. We are going to create transfer functions for digital filters. We are going to create. We are going to create. We are going to be able to get the what do you call them? I'm looking for those terminologies. The values of each, the amplitude value of each frequency component in a signal. I mean, to create filters. Yeah. So that is a complex plane with imaginary z and real z, and that is the unit circle. This will become very important for us, the unit circle. When it comes to the Z transform, the unit circle is very important. So some signals may cause output. Yeah. We are going to look at the region of convergence. Yeah. That is the regions where values for which Z transform exists. That's what we are calling the region of convergence. And we'll be looking at the region of convergence of the Z transform. Yeah. Because that can tell us more about the signal which we have taken the Z transform for. Yeah. So we are going to look at the region of convergence for given xn. is the range of Z for which the transform converges. Yeah. Yeah. So this is what we are going to look at. Remember the transform, Z transform is a power series. Yeah, Z to the minus N. Yeah. It's basically a power series. Yeah. And they can either diverge or converge. So the properties of ROC, regional convergence of Z transform, these are the properties which give us very important information. The first one is the region of convergence cannot contain any poles, because poles is when the xz will be infinite. Yeah, the ones that make xz infinite. Yeah, those are the poles. Yeah, the and the zeros are the ones that make it zero. So the region of convergence cannot contain any poles. The region of convergence is a ring or disk in the z plane centered at the origin. Yeah, in this plane it will be a disk. Remember, in the Laplace transform, I think is a y-axis line. So you'll be talking about what is on the left and what's on the right. Then you'll be talking about what is outside the circle or what is inside the circle. Yeah. The region of convergence of Z transform contains, yeah. So this is another important property of region of convergence, is that the Z transform of an LTI stable system contains the unit circle. Yeah. This part must be part of the region of convergence. Yeah. So what we are saying is the region of convergence of the Z transform gives us very crucial information about that system. Yeah. What else do we need to know? When the Z transform is rational, then its ROC is bounded by poles or extends up to infinity. If Xn is an infinite duration causal sequence, then its ROC is bound, I mean, the magnitude is greater than A. That means it is on the exterior of this circle. Yeah, exterior of the circle. Some as what we are saying is exterior of A, and of course for a stable system, that A has to include the unit circle. Yeah. I think this will be clear when we work with examples. If Xn is an infinite duration anticausal sequence, then not non-causal, anticausal, which means it is only defined on uh, the left of the y-axis. Yeah. And in that case, the magnitude of z will be less than b. That is, it will be the interior of the circle of radius b. Yeah. Of course, the value of b will depend on the sequence, and the value of a in this case will also depend on the sequence. Yeah. So I think we can stop there. You can post your station on the chat. Are there any questions so far? We have not covered much, but probably you already have questions so far. If you don't have any questions, then we are going to continue in the afternoon from where we have just left.